AI-powered enterprise resource planning. Book. By Pradeep K. Suri. Author and researcher. Chapter 1. Exploring AI technologies. Introduction to Artificial Intelligence and its subfields. Artificial intelligence, AI, is a branch of computer science that focuses on creating intelligent machines capable of performing tasks that typically require human intelligence. These tasks include understanding natural language, recognizing objects and patterns, making decisions, and solving complex problems. AI can be classified into several subfields, each with its own specialized area of study and application. 2. AI-powered enterprise resource planning. Machine learning, ML. Machine learning is a subfield of AI that involves developing algorithms and models that enable computers to learn and improve from data without being explicitly programmed. It focuses on the development of mathematical models and techniques that allow systems to automatically learn patterns, make predictions, and take actions based on data. Deep learning. Deep learning is a specialized form of machine learning inspired by the structure and function of the human brain's neural networks. It involves the use of artificial neural networks with multiple layers to process and learn from large amounts of data. Deep learning has achieved remarkable success in various areas, such as image and speech recognition, natural language processing, and autonomous driving. 3. AI-powered enterprise resource planning. Natural language processing, NLP. Natural language processing is a subfield of AI concerned with enabling computers to understand, interpret, and generate human language. It involves techniques to process and analyze text and speech, enabling applications such as language translation, sentiment analysis, chatbots, and voice assistants. Computer vision. Computer vision is focused on enabling computers to understand and interpret visual information from images or videos. It involves developing algorithms and models to extract meaningful insights from visual data, such as object recognition, image classification, object tracking, and image generation. Robotics. Robotics combines AI with mechanical engineering to create intelligent machines capable of interacting with the physical world. It involves designing, building, and programming robots that can perceive their environment, make decisions, and perform tasks autonomously or with human assistance. Robotic systems find applications in various domains. 4. AI-powered enterprise resource planning, including manufacturing, healthcare, exploration, and assistance. Expert systems. Expert systems are AI systems that mimic the decision-making ability of human experts in a specific domain. They are built using knowledge bases and rule-based reasoning to provide solutions, recommendations, and expert-level insights in areas such as medicine, finance, and engineering. Reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions and take actions in an environment to maximize a reward signal. It involves training an agent through trial and error, with the agent receiving feedback in the form of rewards or punishments based on its actions. Reinforcement learning has been successful in applications such as game playing, robotics, and autonomous systems. These subfields of AI often overlap and complement each other in solving complex problems. AI technology continues to advance rapidly, and its applications have the potential to revolutionize various industries, from healthcare and transportation to finance and entertainment. Machine learning, ML, and deep learning, DL, are two important subfields of artificial intelligence, AI, that focus on enabling machines to learn from data and make intelligent decisions. While they share similarities, they differ in their approach and complexity. Machine learning is a subset of AI that involves the development of algorithms and models that allow computers to learn and make predictions or take actions based on data without being explicitly programmed. ML algorithms are designed to automatically learn patterns, relationships, and 5. AI-powered enterprise resource planning. Insights from large amounts of data. Here are some key points. About machine learning. Learning from data, ML algorithms learn from historical or labeled data through a process called training. During training, the algorithm analyzes the data, identifies patterns, and adjusts its internal parameters to optimize its performance. Supervised and unsupervised learning, ML can be categorized into supervised and unsupervised learning. In supervised learning, the algorithm learns from labeled data, where each input is associated with a corresponding output. In unsupervised learning, the algorithm discovers patterns or structures in unlabeled data without explicit output labels. Feature engineering, ML often requires feature engineering, which involves selecting and transforming relevant features from the input data to improve the algorithm's performance. This step is crucial for representing the data in a way that captures the underlying patterns effectively. Broad applications, ML has diverse applications, including spam filtering, fraud detection, recommendation systems, image recognition, and natural language processing. It can be applied across various domains and industries to automate processes, make predictions, and extract insights from data. Deep learning is a subfield of ML that focuses on artificial neural networks with multiple layers, inspired by the structure and function of the human brain. Deep learning models, also known as deep neural networks, are capable of learning and representing complex patterns in data. Here are some key points about deep learning. Neural networks, deep learning models are composed of interconnected layers of artificial neurons called neural 6 AI-powered enterprise resource planning networks. Each layer processes and transforms the data, extracting increasingly abstract and hierarchical representations. Representation learning, deep learning excels in automatically learning meaningful representations of data. Instead of relying on handcrafted features, deep neural networks learn feature representations directly from the raw data, enabling them to capture intricate patterns and relationships. Deep neural network architectures, deep learning includes various architectures, such as convolutional neural networks, CNNs, for image and video data, recurrent neural networks, RNNs, for sequential data, and transformers for natural language processing tasks. These architectures have achieved remarkable success in tasks like image recognition, speech synthesis, language translation, and more. Training with big data, deep learning models require significant amounts of labeled data for training, and they thrive on big data. Training deep neural networks is computationally intensive and often requires specialized hardware, such as graphics processing units, GPUs, or tensor processing units, TPUs, to accelerate the computations. Deep learning has made significant advancements in areas like computer vision, speech recognition, and natural language. 7. AI-powered enterprise resource planning. Processing. It has demonstrated state-of-the-art performance in many AI tasks and has contributed to breakthroughs in areas such as autonomous vehicles, medical diagnostics, and game playing. In summary, machine learning provides the foundation for training models to make predictions and decisions from data, while deep learning, as a subset of ML, focuses on complex neural networks with multiple layers, enabling them to learn hierarchical representations and handle more sophisticated tasks. Natural language processing, NLP, and computer vision, CV, are two distinct but interconnected fields of artificial intelligence. AI that deal with the understanding and processing of human language and visual information, respectively. Although they have different focuses, there are several areas where NLP and CV can intersect and complement each other. Let's explore them in more detail. Image captioning. Image captioning combines CV and NLP to generate textual descriptions of images. CV techniques are used to analyze the visual content of an image, while NLP models are employed to generate coherent and descriptive captions based on the visual information. Visual question answering, VQA systems allow users to ask questions about images, and the system generates answers based on both the visual content and the textual input. CV techniques are used to understand the visual elements, while NLP models interpret the question and generate relevant answers. Sentiment analysis in visual data. By combining CV and NLP, it becomes possible to analyze sentiments or emotions expressed in visual content, such as images or videos. CV techniques can 8. AI-powered enterprise resource planning. Identify facial expressions, objects, and scenes, while NLP models can analyze text captions or comments associated with the visuals to determine sentiment. Text extraction from images. NLP can be used in conjunction with CV techniques to extract text from images. Optical character recognition, OCR, is a common CV task that recognizes and extracts text from images, and NLP techniques can further process and understand the extracted text. Visual sentiment analysis. NLP models can analyze textual descriptions or comments associated with images to determine sentiment, and CV techniques can analyze visual features such as colors, facial expressions, or scene composition to infer emotions or sentiments related to the image. Multimodal models. Multimodal models combine both CV and NLP modalities to jointly process and understand information from different sources, such as images, videos, and text. These models enable a deeper understanding of the relationships between visual and textual information, opening up possibilities for applications like image-text matching, visual grounding of textual concepts, and more. These are just a few examples of how NLP and CV can intersect and be mutually beneficial. As research progresses, the integration of these fields continues to evolve, leading to more advanced applications and technologies that can leverage both textual and visual data. Reinforcement learning, RL, and generative models are two important subfields of artificial intelligence that have distinct objectives but can also be combined to address various challenges. Let's explore the relationship between RL and generative models. 9. AI-powered enterprise resource planning. Reinforcement learning. RL is a machine learning paradigm where an agent learns to make sequential decisions in an environment to maximize a reward signal. The agent interacts with the environment, takes actions, receives feedback in the form of rewards, and updates its policy to improve its decision-making process over time. RL has been successfully applied in a wide range of domains, including robotics, game playing, autonomous driving, and more. Generative models. Generative models are machine learning models that learn the underlying distribution of a given data set. Their goal is to generate new samples that resemble the original data distribution. Generative models can be probabilistic, such as Gaussian mixture models, GMMs, and variational autoencoders, Vs, or based on adversarial training, such as generative adversarial networks, GANs. Combining reinforcement learning and generative models. There are several ways in which RL and generative models can be combined. Generative adversarial imitation learning, GALE. combines generative models, specifically GANs, with RL. It uses a discriminator to compare the agent's behavior with an expert's behavior and provides rewards based on the similarity between the two. The generator of the GAN learns to mimic the expert, and the RL algorithm optimizes the policy based on these rewards. Generative adversarial networks for RL GANs can be used to generate synthetic samples as training data for RL agents. This 10 AI-powered enterprise resource planning helps in data augmentation and exploration, enabling the RL agent to learn from a wider range of experiences. Augmented random search, ARS is a model-free RL algorithm that uses a generative model to approximate the policy. The generative model samples actions and the RL agent collects rewards by executing those actions. The RL agent then uses the rewards to update the policy and improve its performance. World models is an RL approach that combines a generative model with a controller. The generative model learns to generate a compact representation of the environment, such as a latent space, and the controller operates in this compressed space. This approach reduces the need for direct interaction with the environment, enabling more efficient RL training. These are just a few examples of how RL and generative models can be combined. The combination of RL and generative models opens up possibilities for learning complex representations, improving sample efficiency, enhancing exploration, and addressing various challenges in reinforcement learning. Researchers are actively exploring and developing novel approaches that leverage the strengths of both RL and generative models to advance the field of AI. AI algorithms and techniques refer to the various methods and approaches used in artificial intelligence to solve problems, make predictions, and learn from data. Here are some commonly used AI algorithms and techniques. Machine learning, ML machine learning algorithms enable computers to learn from data and make predictions or take actions without being explicitly programmed. Popular machine learning algorithms include decision trees, random forests. 11 AI-powered enterprise resource planning. Support vector machines, SVM, naive Bayes, K-nearest neighbors, KNN, and neural networks. Deep learning is a subfield of machine learning that focuses on training artificial neural networks with multiple layers, deep neural networks, to learn representations and patterns from large amounts of data. Convolutional neural networks, CNNs, are commonly used for image recognition, while recurrent neural networks, RNNs, are used for sequence data like natural language processing and speech recognition. Reinforcement learning, RL reinforcement learning involves training an agent to learn optimal actions in an environment by trial and error. The agent learns through positive rewards and negative punishments, aiming to maximize cumulative reward over time. Popular RL algorithms include Q-learning, deep Q networks, DQN, and proximal policy optimization, PPO. Natural language processing, NLP. NLP focuses on enabling computers to understand and generate human language. Techniques include sentiment analysis, named entity recognition, text classification, machine translation, and question answering systems. NLP algorithms often involve techniques like word embeddings, example word2vec, glove. Recurrent neural networks, RNNs, and transformers, example BERT, GPT. Genetic algorithms are inspired by the process of natural selection and genetics. They involve evolving a population of potential solutions to a problem over multiple generations. The best individuals are selected for reproduction, and their traits are combined and mutated to generate new solutions. Genetic algorithms are often used for optimization and search problems. 12 AI-powered enterprise resource planning. Bayesian networks. Bayesian networks are probabilistic graphical models that represent uncertain relationships between variables. They use Bayesian inference to update beliefs about variables given observed evidence. Bayesian networks are widely used for probabilistic reasoning, decision-making, and prediction in domains with uncertainty. Support vector machines, SVM. SVM is a supervised learning algorithm that can be used for classification and regression tasks. It finds an optimal hyperplane that separates data points of different classes with the largest margin. SVMs can handle both linear and nonlinear decision boundaries through kernel functions. Ensemble learning. Ensemble learning combines multiple individual models to make predictions. It aims to improve the overall performance by leveraging the diversity of different models. Examples include bagging, example random forests, and boosting, example AdaBoost, gradient boosting machines. These are just a few examples of AI algorithms and techniques. There are many more specialized algorithms and variations within these categories, and new techniques are continuously being developed as the field of AI evolves. Thank you.